Welcome, my name is Guillaume Fournier, and today I will be presenting our research on low-order modeling to investigate clusters of ITA modes in annular combustors. This work was carried out at the Technical University of Munich, and I would like to acknowledge the European Union for funding this research with the project Annulite. Thermoacoustic instabilities, as we know them, result from interactions between the unsteady heat release of a flame and the acoustics. We consider a fluctuating flame. It will act as a source of sound. We call F a wave traveling in the downstream direction and G an acoustic wave traveling in the upstream direction. The flame will usually be placed in a confined environment to extract either mechanical work or thermal energy. Therefore, the flame will interact with its acoustic environment. At the location of the flame, there is a temperature discontinuity, which means that the acoustic waves will be partially transmitted and partially reflected. As we just mentioned, the unsteady heat release also contributes to the outgoing waves. For a velocity-sensitive flame, the unsteady heat release Q dot prime is directly controlled by the upstream velocity U prime through the flame transfer function. But the upstream velocity U prime directly depends on the acoustics F and G. Therefore, we can see that the unsteady heat release will directly perturb the upstream velocity with this intrinsic feedback loop that we call the ITA feedback loop. That was shown by Bamberg in 2015. And because of this ITA feedback loop, a thermoacoustic instability can manifest itself even in an anechoic environment. That was shown by Hoymakers in 2014. The ITA mode in a non-reflecting environment can be determined analytically. Emmert showed in 2015 that the frequency and the growth rate of the mode directly depends on the time delay of the flame, on the interaction index of the flame, of the normalized temperature ratio, and of the ratio of specific impedances. In annular combustors, ITA modes create clusters, which means we have modes with very close frequencies but different growth rates. Here is a picture of Buschmann of 2020, where he showed that for the mica burner we can find 3 clusters. The ITA modes of various mode order will align around the pure ITA frequency, which is the frequency of the ITA mode in an anechoic environment. So the question we want to address today is, why do we find clusters of ITA modes in annular combustor? Can we explain the structure of the spectrum? To answer that question, I will divide my presentation in 4 parts. First of all, I will introduce the network model that we used and show how we can transform it into an equivalent burner. Then we will explain the origin of the clusters, and we will explain the spectrum structure with means of a Phasor analysis. So let's start with the network modeling. We consider a typical annular combustor with its plenum, burner tubes, and chamber. Such combustor exhibits a discrete rotational symmetry, which means that we have a number of identical sectors that we call unit cells. According to Bloch wave theory, the eigenmodes of the system can be computed by considering a single unit cell. In the frequency domain, the solution of the acoustic pressure field P hat for the entire domain can be written as psi, a function that is periodic and identical in each unit cell and a phase shift. M is the Bloch wave number, and n is the degree of discrete rotational symmetry, so in our case the number of burners. We can therefore reduce our study to a single unit cell and apply Bloch boundaries. We further reduce the complexity of the system to obtain a system as simple as possible. We first assume no mean flow in the azimuthal direction, which means that we have a reflection symmetry, and therefore we can consider only half of the Bloch wave numbers. The other hypothesis is that we decouple the plenum, as it can often be the case, and we replace it by an open end. Such configuration can be modeled with a low-order network model. For that, we need only two more hypotheses. The first one is that the axial and radial length are negligible compared to the azimuthal direction, which means that the radial and mixed modes will occur at higher frequencies and therefore are out of the scope of this study. We also consider the outlets to be choked, which corresponds to a u prime equals 0 for small Mach numbers. And therefore, such system can be modeled with the following network model. We have the pressure node upstream, the burner tube, a flame, a T-junction, and two ducts that model the annular chamber. Now, let's see how we can transform this model into an equivalent burner. The annular combustor can be transformed into a longitudinal burner. If we replace the two ducts that model the annular direction and the T-junction by an equivalent reflection coefficient Rm, we obtain the following longitudinal burner. The equivalent reflection coefficient depends on several parameters that are frequency, mode order, and geometrical parameters. We define the equivalent reflection coefficient as the ratio between the G wave coming back from the chamber and the F wave coming in the chamber. I'm not going into the details of the derivation here, you can find that in the paper, but we obtain the following analytical expression where the Helmholtz number is KL and alpha is the area ratio between the burner and the chamber. We can see that this reflection coefficient depends on the frequency hidden in the dimensionless Helmholtz number, on the azimuthal order, and of geometrical parameters. Note that in the Helmholtz number is hidden L, the distance between two burners. We can prove that the gain of the reflection coefficient is 1. However, the phase is not trivial. We can see that we have a frequency dependence and also the phase of the reflection coefficient will change with the mode order. For example, we can see that the axial mode m equals 0 start at phase 0 and all other mode will start at phase pi. And they have the same pattern, switching from pi to minus pi and crossing the 0 line exactly at the location of the passive acoustic modes of the annular chamber. The reflection coefficient will also strongly depend on the area ratio alpha. You can see here the full line that represents the first azimuthal order and the dashed line that correspond to the azimuthal order n over 2. The color indicates the area ratio. We can distinguish two interesting limit cases. The first one, when alpha is really small, so that corresponds to this blue line, which means that the area of the burner is really small compared to the area of the chamber. We can see that the phase is almost pi, which corresponds to a reflection coefficient more or less -1. That models an annular combustor, a duct terminating in a large vessel. On the other hand, when alpha is really large, which corresponds to a burner area very large compared to the chamber, the phase is almost 0, which corresponds to a reflection coefficient of 1. That would model a can annular combustor with a crosstalk close to the turbine inlet. Therefore, the annular combustor can be transformed into n over 2 plus 1 subsystems that are simple longitudinal burners that will differ only by their outlet boundary condition. Now we will have a few considerations on the clusters. In a typical lab-scale combustor, the ITA and the acoustic modes are not in the same frequency range. We consider this combustor with 12 burners. The length of the burner tubes is of the order of magnitude of 1 or 2 cm, whereas the length of the chamber is 60 cm. We describe the flame with the classic n-tau model. With those parameters, the ITA frequency is at 250 Hz, whereas the first azimuthal chamber mode is around 1000 Hz, which means that those two modes are far away from each other. In the frequency range of interest, the phase of the reflection coefficient shows a linear dependency on frequency. So this was the plot of the phase of the reflection coefficient for the dimensionless Helmholtz number. But in our case, if we zoom in the frequency range of interest between 0 and 400 Hz, we can see that for every mode order, the phase is a straight line. And a phase changing linearly with the frequency is typical of a system with a constant time delay, such as a duct. Indeed, if we write the equation of the phase, we have pi minus a constant coefficient times frequency. This constant coefficient will be different for every mode order since we have different slopes. Knowing the phase and the gain being 1, we can write that the reflection coefficient is minus exponential minus I to k Lm, which means that the equivalent reflection coefficient can be replaced by a duct of length Lm that terminates with an open end. Therefore, our initial annular network model is now reduced to n over 2 plus 1 Rieke tubes. So instead of having a complex outlet boundary condition, we now obtain simple ducts and an open end. The models differ only by the length of their equivalent duct. So for low azimuthal order, we have rather large ducts, and for higher azimuthal order, we have smaller ducts. For a Rieke tube with fully reflecting boundaries, away from the passive acoustic modes, ITA trajectories are straight lines. So this is a picture from Occhini that shows that when varying n, the interaction index of the flame, the ITA trajectories are straight lines. In the region of the passive acoustic mode, this is not the case anymore. We observe peculiar trajectories involving exceptional points, but this is out of the scope of this study. The main takeaway here is that away from an acoustic mode, the ITA will remain close to its pure ITA frequency. If we go back to our case, since the ITA mode and the acoustic modes are far away from each other, they do not interplay, which means that for every azimuthal order, the ITA modes will remain close to their pure ITA frequency, thus creating clusters. It is interesting to notice the structure of the spectrum. We can see that the higher the azimuthal order, the more damped the mode is. We will now use Phasor Analysis to explain this spectrum structure. Phasor Analysis is a convenient tool to study harmonic signals. Let me briefly introduce the concept. So if we consider a harmonic fluctuation y, that is a cosine of amplitude A, of frequency omega, and of phase phi, this can be seen as the real part of the following complex function a exponential I omega t plus phi. In the complex plane, that corresponds to a rotating vector of length a, the magnitude of the signal, rotating at the speed omega with respect to time. However, a constantly rotating vector is not very helpful for an analysis at an arbitrary time instance. Therefore, we can factor out the time dependency and keep only the first two terms, a exponential I phi. This complex valued vector is what we call the phasor. In the complex plane, it corresponds now to a fixed vector of length a, the amplitude of the signal, and of angle phi that corresponds to the phase shift. The phasor analysis can be used to explain the spectrum structure. We consider the equivalent Rieke tube of a mode of low azimuthal order, which means that we have a rather large LM equivalent duct. We need one more hypothesis, which is that we have a marginally stable mode, which allows for phasors of fixed length. At the inlet, the phasors must satisfy the boundary condition. Since we have a pressure node that imposes F plus G equals 0, we therefore have the vectors pointing in opposite directions. When traveling along the burner tube, from the inlet to the upstream location of the flame, the phasors will rotate by an angle phi u that depends on the frequency and the length, and that represents the phase shift. So we have the rotating phasors, and Fu and Gu are the phasors upstream of the flame. Pressure and velocity are therefore known. Recall that P prime equals F plus G, and U prime equals F minus G. The same analysis can be performed from the outlet. However, there we do not know in advance the length of the phasors F out and G out, only their direction, since they must also satisfy the boundary condition. When traveling along the equivalent duct, the phasors will rotate also by an angle phi d. However, note that here the direction of the rotation is the opposite, since we travel in the upstream direction. At the flame, the jump conditions must be satisfied. Recall the Rankine-Hugoniot jump equations that gives pressure continuity, and that the downstream velocity is equal to the upstream velocity plus the heat release. Therefore, we can use this jump condition to geometrically construct the phasors Fd and Gd downstream of the flame. And knowing that F minus G is the velocity, we obtain the velocity downstream of the flame, and therefore with the Rankine-Hugoniot equation we also obtain the heat release. The heat release rate will change with the azimuthal order. The higher the azimuthal order, the higher the heat release rate. Now we consider a higher mode order M. That translates into a smaller equivalent duct Lm. Therefore, the phasors from the outlet will rotate with a smaller angle phi d. So let's go back to the phasors plot. We rotate from the outlet with a smaller angle. But since the jump condition must still be satisfied, we obtained phasors that are longer. Which means that now the downstream velocity of the flame is higher, which implies that the heat release rate will be more important. So the higher the azimuthal order, the higher the heat release rate. And that fully explains the spectrum structure. We assumed modes that are marginally stable, and the higher the azimuthal order, the higher the heat release required to stay at the neutral curve. Said differently, for a given unsteady heat release, eta modes with a higher azimuthal order are more damped, which is what we observe on this spectrum. To summarize, here are the four main takeaways of this presentation. The annular combustors can be described with low-order network models. By using Bloch wave theory, an annular configuration can be reduced to n/2+1 subsystems that are simple longitudinal burners. When the acoustic and the eta modes are far away from each other, they do not interplay. Therefore, the eta modes will remain close to their pure eta frequency, thus creating clusters. The Phasor analysis helps us to understand the spectrum structure. Modes with higher azimuthal order are more damped. Thank you for your attention. If you have any question, I will gladly answer them during this live Q&A.